Hi everyone. I'm glad to share our work, HybridRepair, towards annotation-efficient repair for deep learning models with you. Despite the much effort spent on developing high-quality models, the model can still fail. The model failures can cause monetary loss or even life risks. Let's look at some examples. On the left-hand side, the NVIDIA DEP2 model, which is a well-known open source model for autonomous driving, is not able to recognize the direction because of the darkness. In the second example, the autonomous driving system chauffeur failed because of the rain. One possible reason for these failures is design time defects. For instance, the training data can be insufficient, dirty, or being maliciously modified. Insufficient training epochs can cause problems as well. Besides, the model used for training can be a weak model that does not have sufficient capacity to learn the task well. Therefore, before deployment, thorough testing and debugging is necessary to ensure functional correctness. In practice, the unlabeled data are often easy to collect, but the labeling cost is often high. With limited labeling resources and the unlabeled data pool, how can we efficiently repair the DNN model? This is what we are going to explore in this work. Existing works, many focus on selecting data for annotation and fine-tuning the model with this additional data. For example, DeepGenie labels the ones that are likely to fail. Some works, such as a Corset, focus on selecting diverse samples, since they believe that sample diversity is important for fine-tuning. MCP and Batch simultaneously consider the failure probability and sample diversity during selection. For these methods, achieving a higher repair rate is inevitably associated with more expensive labeling costs. Alternatively, with a large amount of unlabeled data, semi-supervised learning is an effective solution for model improvement. For example, mix-match improves the model accuracy by encouraging the model to have consistent prediction on each unlabeled sample and their augmented version. For example, this is an augmented version of the bird. They have similar semantic meanings, so the model should produce consistent results for them. We find that the model prediction quality on input samples is related to the local entropy. We know that we can calculate the prediction entropy for an input X if we know the prediction probability for X. Now, the local entropy is defined by the entropy of the averaged prediction probabilities for X and its augmented neighbors, Nx. As we can observe from this figure, the prediction quality decreases with the local entropy values. This metric can help us to locate the poorly trained regions. To further motivate our method, on the one hand, we observe that directly applying existing SSL techniques for model repair can be problematic. To illustrate, we show the repair results when unlabeled samples of different local entropy values participated in repairing. We observe that when there is a distribution shift between the training and the field data, the accuracy after fine-tuning decreases when the unlabeled samples with higher LE values participate in fine-tuning. Applying consistency regularization on all unseen unlabeled data can even hurt the original performance. For example, the accuracy drops from 78% to 72%. On the other hand, we already showed that the high LE value regions often have lower prediction quality. Now, in this figure, we show that the low quality is related to the sparse training samples in these regions. Therefore, to achieve high accuracy, we need accurate yet sufficient labeled training samples. Motivated by the above, we propose to combine the utilization of the unlabeled data and labeled data for model repair. For unlabeled data, our main goal is to address their positive impacts and suppress their negative impacts. With the limited labeling budget, our goal is to selectively annotate some samples to obtain accurate yet sufficient labeled data. The final loss function of our method contains two parts: the consistency loss evaluated for the unlabeled data and the standard cross-entropy loss evaluated for the labeled data, including the original training data and the newly labeled data. The lambda is a hyperparameter that balances these two losses. To leverage unlabeled samples for training, we propose a simple yet efficient algorithm. First, we calculate the local entropy values for all unlabeled samples. Second, since the quality of the unlabeled data decreases with local entropy values, we can select unlabeled samples by setting a threshold. Last, since the samples with lower local entropy values are more beneficial for repair, we highlight these samples with larger weight. The weight is set as 1 minus the local entropy value. With this sample selection and weighting method, the positive samples are emphasized and the negative samples are removed. Under the given labeling budget, we propose a region labeling technique that selectively annotates data. First, we project the samples from the input space to the feature space, which has a lower dimensionality. The similarity between samples is easier to measure in the low-dim space. Second, we remove those samples located in sparse regions, and we cluster the remaining samples into many local dense regions. Label samples in dense regions are more cost-effective than in sparse regions. The reason is that since there are many similar samples in a dense region, we can propagate labels to similar samples, taking advantage of the fact that neighboring samples often have the same label. We apply existing clustering algorithms such as dbScan and k-means++ for this step. Then we rank each region with an estimated prediction quality and prioritize the low quality regions since repairing them brings more benefit than repairing well-trained regions. At last, under the given labeling budget, we annotate one sample for each region and propagate the label to other samples in the region. In this way, the training data density for poor regions can be increased. This is our setting. We evaluate our method on 3 popular data sets: CIFAR-10, SVHN, and GTSRB. So we use 3 models for each data set: model A, B, and C. Model A is a setting that the training and testing data are in the same distribution, while model B and C. Well, for model B and C, their training and testing data set have some distributional shift. We compare our method with DeepJourney, MCP, Corset, and batch methods. We also compare our method with semi-supervised learning and active learning methods. Now, we compare HybridRepair with these baselines. In this experiment, we use various badges and models. We have the following observations. First, in general, HybridRepair consistently improves the model accuracy after repairing and outperforms the baselines in all datasets and models. Second, the performance of the two semi-supervised learning-based methods are not stable. These methods can downgrade the model performance sometimes. In contrast, HybridRepair can improve the model accuracy even if under distributional shift scenarios. There are more results about this. So HybridRepair can consistently outperform other methods in all budgets. We show that when only using the unlabeled data for repair, the mix match can hurt the model performance when there is a distributional shift. In contrast, our method can effectively emphasize the positive impact and suppress the negative impact of the unlabeled samples. We visualize the selected samples by different methods to understand why HybridRepair performs better. We use a model whose training and testing data has a distributional shift to produce this figure. We set the budget to 1% as we can observe. First, one major problem of this model is the lack of training data in the bottom left corner, leading to many misclassifications in these regions. Only MCP, Genie, and our method pay attention to these regions. Further, since we apply region labeling technique to the selected samples, we increase the training data samples. We increase the training sample density in these regions. Hence, HybridRepair can accurately locate the failure regions and ensure sufficient training data in these regions, which makes it stronger than others. HybridRepair has two major limitations. First is the runtime cost. As we can observe, HybridRepair has more runtime compared to other methods, either active learning, traditional repairing methods, or active learning and semi-supervised learning methods. Also, HybridRepair requires extra feature extractor. To summarize, HybridRepair combines the use of a small amount of labeled data and a large amount of unlabeled data for repair. For unlabeled samples, we propose a simple yet efficient. For unlabeled samples, we propose a simple yet effective method to select positive samples and address high-quality samples. We also propose a region labeling technique that can selectively annotate sufficient labeled data under a given labeling budget. Experimental results show that HybridRepair outperforms existing methods. Thank you. If you have any questions, please ask.